Okay, let's do announcements. So the big assignment for this week is the mission checkpoint. So this is on Canvas. It's due September 1st. We're trying to keep this a hard deadline because we have to sort through all these and give you feedback. So we're only asking if you have a extremely extenuating circumstance, then you can have an extension, but we're asking you to please try to honor this if at all possible. We'll do flash talks today to keep getting to know each other. So after class today, we will have these students going, and then after class tomorrow, we have a few more. And the Canvas submission is still open, so you are welcome to continue submitting flash talks so we can get to know each other. There's a new form on Canvas under the certificates module. So if you want an astrobiology certificate, we need you to fill out this form. So it's very straightforward, just asking your name, your affiliation, and to make sure you understand the rules. So we ask you to please fill that out. The deadline is next week sometime. So then in addition, I just want to have some housekeeping for if you have questions and problems. So if it's a question or problem that other students may be having, then go to the Discord and post in general questions so then everyone can read the question and the answer. If it's really specific to you or your team, then you can either email us, we are monitoring this very regularly, or you can send a message on Canvas, which is kind of a convoluted pathway. So either of these will go to the same place, so it doesn't really matter. And we ask if you have an extreme circumstance and need an extension, we're pretty understanding, but it's much more helpful for us to know before the deadline instead of a few days after. So that's our housekeeping. And then I am really excited to introduce Dr. Theiling today, who will be speaking to us about fieldwork. So Dr. Theiling is a research scientist and geochemist at NASA Goddard Space Flight Center. She works on mass spectrometry for ocean worlds, such as Europa and Enceladus. And she does a lot of laboratory analog experimentation. And she also develops spaceflight instrumentation, works with data processing techniques and artificial intelligence. And she's also conducted fieldwork around the world, including in the US, in Spain, in Hungary, and Jordan. And she most recently was in the Canary Islands to work on fieldwork there, which is a really unique environment that's very different than anywhere else on Earth. So today she will talk to us about how astrobiology fieldwork can support NASA missions. And we're really excited to host you. So thank you for joining us, Bethany.
Well, thank you for having me. I'm really excited to talk to you guys. And this is just such a cool idea. So I'm glad to see that this mission concept development activity is something that you all are working on. So hi, yeah, my name is Bethany Theiling, and great introduction. So thank you very much, Tess. I know you guys have a Discord that you usually do your communications on, and please feel free to do I have some interactive activities that I had planned. We'll see how it works. Feel free to do that through the Discord if that's what makes you feel more comfortable. I also have a Slido set up. So if you go to this website, and I set it up so that basically, I know everybody's got their phone next to them. So if you want to have this up on your phone, I've got just a couple of little things that we can play around with. I have an event code here that's 1401069. And it's just a way for us to kind of interact in a different way. I know that sometimes these virtual experiences can be a little flat. So I'm hoping to lift a little bit of energy. I know that there are people from around the world, so hopefully this will give you a little boost if it's morning, afternoon, or night for you. So I've got in the background here, I'm trying to think about not just astrobiology, but also planetary, and many planetary environments could potentially host life. We don't know because we have one data point, and that is Earth. Earth is our data point for where life lives. And so we kind of have to evaluate that context, and we're constantly changing our idea about where and how life might have evolved. So it's a good thing to kind of keep your mind open. So I want to give you a sense today of not just astrobiological things that we could do in the field, and I want to kind of push your minds too right there at the end, but I want to also give you a sense of the breadth of things that can be done as planetary analogs on Earth. So I'm actually showing you in the background here, this is an image of Lanzarote, one of the field sites that we were in. So I want to give you this sense of this, to many people, this looks like Mars. The difference is that there are these big clouds in the background. Currently, they are not dust, but there are great dust storms on Lanzarote as well. So this is one of the Canary Islands, and I'll talk a lot more about that. I'm going to focus on that place today. So let's start with the Slido. Hopefully you'll have a chance to get that going by now. And I'm going to give you just a moment in case you're still working on it or still signing on. So once I pick up this image, in a word or short phrase, what do you think are the most striking features of this image, and I've just released the question on Slido, so you should be able to populate it. So I'll give you like 15 to 30 seconds. There's no right or wrong answer, just what pops into your mind when you see this. Okay, so this should be visible to you all now, and you should be able to see if you're here, that there's a word cloud that's popped up and visible. So you should be able to see things like the most common answer was crater, so it's in the biggest one in the middle. Moon was another one. There's a lot of different things here, so I'm going to just sort of pop through these. Concave hills, so I'm going to point out like this is the concaveness part of that. Land bumps, so these are the bumps right here, so there's a lot of those. Dune structures, looks like a crater, but from the opposite side. That's a really good one, actually. Smooth surfaces, yeah, there are some smooth surfaces in here. Mountains, mons, sediment, there's probably sediment. Sediments and dunes, actually there appear to be some like really nice dunes up in here, so that's interesting. Perfect circles, some of them are pretty close to being perfect circles, I agree. Similar, Olympus, so someone is making an interpretation there, that's also cool. Hills flattened by craters, volcanic activities in craters. This is great. So we could continue on this all day, but I want you to start thinking about the kinds of processes that could form these. So this is the kind of thing, I'm not telling you where this is from. This could be from Earth. It could be from the moon. It could be from Mars. It could be from Mercury. So there are a lot of things here, and I will tell you where it is in a moment. So hold on. But there are a lot of processes being represented here. And I think it's a really great thing to take a step back and say, okay, what is important about what I'm looking at? Sometimes I'm looking for something specific, but sometimes it's good to just step back and say, what am I actually seeing here without placing a lot of constraints on that interpretation? So I'll go to the next one. And I have a multiple choice on Slido. So I'll release this one next. Oops, I'm on the wrong screen. Okay, so what you're seeing here, and I will release this one, which one is Mars? And your options are right or left. And I'll only give you like maybe 15 seconds for this. Only one of these is Mars. And Tess, if there's anything coming up on Discord, let me know too, if you could.
Will do.
Okay. All right, I'm going to go ahead and show these results. I'm not going to close it, so you could change it if you wanted to, but this is impressive to me. So it seems like almost 50-50. We've got 52% say the right-hand figure is Mars, 48% say the left-hand figure is Mars. Would anyone be willing to maybe type into Discord why you think one versus the other? Let's go with right, the right-hand side. Why is the right-hand side Mars? Or the left-hand side being Mars? Sorry.
A few people typing.
Nice. It's all going to come up at once. I'm guessing, I'll just fill the space a little bit here. So I'm guessing that many of you are picking up on the similar features, right? So you have those circles, you have the mounds, things that were in our word cloud, right? Maybe you're identifying those flat spaces that are in between. Do we have any coming up yet, Tess?
Yeah, so some people are saying that there maybe looks like there's a water path, or that the left-hand side seems like an elevation seen on Mars. Another says the terrain pattern. Someone said that the left side looks so smooth it doesn't feel like Mars. And then someone else is saying the right side looks like it was geologically active. So a lot of different ideas.
That's a lot of it. And I'm going to applaud you all, because these are all really great observations of this place that maybe you don't know the answer to. So I'll put up the answer. Keep going on the wrong screen. Here we go. So left-hand side is Earth. I totally agree. It looks like Mars. I could not get a feed on like whether this was like what instrument this was from, but I think it's from Landsat. And this is a black and white version. It also kind of messes with the mind because the resolution is a little bit low, which we know on Earth we have very high resolution images. So it's sort of strange to see such a low resolution image. But this is actually the Canary Islands. I'm going to take you on a little bit of a tour of some of these places, actually. So you'll be able to see these in real life. On the right-hand side, we have an image from the Mars Reconnaissance Orbiter, or MRO. And all these features are really interesting. So yeah, there's these dune forms. This looks really flat. And I think the observation that maybe like it's too flat to be Earth, and this is interesting because the volcanic flows on Lanzarote are in the Canary, this is part of the Canary Islands, are so new that you haven't had the opportunity to form these dune fields yet. So you just don't have, it's very young. Whereas maybe the surface here is much older and you have a lot of dust that can form and accumulate. So it's really interesting to see that pattern. All right, so I'm going to keep the multiple choice is going to continue to be up, so you can change your answers on the next one, or you should be able to, as long as it works the way that I think it is. I'm going to turn off the results so you can't see it. So next one, which one is Mars, left or right? Okay, I'm turning on the results. Pretty good job this time. So the left-hand side is in fact Mars. This is Montracou, and the right-hand side is Coyote Buttes, and this is the reason it's such a low resolution picture is because I didn't take it. I just took it off the internet. This is a very famous outcrop in Utah, and also a very famous outcrop on Mars. So many of you may have even seen pictures of this floating around on the internet because it's a pretty famous image. So one of the things that I want to get across to you all, like you're picking up on like the fact that there are similar patterns and you can have similar things. I probably could have found one that looks more like Mars. I know I've been to one on Earth that looks more similar to this. I just couldn't find the image in time. But they're like, these are the same kinds of things that we think about too, as planetary scientists and as astrobiologists as well. So I'm going to do one more. I'll keep it open. Which one is Mars? And I should say, while you're figuring that out, the last image was of dune fields. So those dune fields that we saw in the first image, you actually have what's called stratigraphy that you can see that's formed both on Earth and on Mars. I see you all are learning. I have a pattern here. Excellent. Nice. Okay, I'm going to go ahead and show this off to you all. Really good job. So 81% of people said that the right-hand side is Mars. 19% said that the left-hand side is Mars. These are intentionally difficult. So, oops. The right-hand side is Mount Sharp. It's also a reasonably well-known image these days. And so basically what you're looking at is that there are these veins that I believe are calcite deposits or some sort of, there's some sort of precipitate, maybe gypsum deposits. And they are harder than the surrounding rock. And so they're actually taking a longer time to weather out. And so you end up getting like they protrude out of it. The same thing has happened in Wind Cave in South Dakota. There are other places. This just happens to be a really famous one on Earth. So what I'm hoping to demonstrate from all these things is that there's scales. So I brought you from like an orbital scale, looking down at these planets and trying to recognize similarities or differences. Then we're looking at kind of outcrop scale, and now we're zooming in, and you can continue to zoom in. So you could continue to look at mineralogy, you could look at molecular patterns. So there are so many scales on which you could do this kind of planetary analog research. And I also wanted to give you this sense of like kind of the importance of doing this, because yes, it's amazing to have these rovers on Mars or on the moon or any other planet that we might visit, or moon that we might visit. But just look at this traverse here. So this is about 11 years worth of distance, and it's about, I think, 15 miles, pretty close to 15 miles. So that's not a lot of space over a lot of time. We love all the things that Curiosity has been able to do, but the reality is that we can't go very far. We have to be able to figure out ways to do exploration that are going to take advantage of being on Earth. So how can we both make more informed decisions when we go to a planet, and also going to do like planetary analog research on Earth really helps us interpret the results that we're getting back from things like, you know, the instruments on Curiosity rover. But that's also called the Mars Science Laboratory. So now I'll start transitioning to the fieldwork that I've done. I could have talked about so many different places because I've done fieldwork in a lot of different places. Like Tess said, you know, I've done fieldwork in the Canary Islands. I've done fieldwork in the southern part of Spain, in Jordan, Hungary, the UK, a lot of places in the US, including Hawaii. and I'm probably forgetting some places. But what I really want to focus on today is my recent expedition to the Canary Islands. And so this was the 2023 GeoLife expedition, and you may see that there are those two things, the geo and the life. We did not specifically go for astrobiology, but because this is a brand new site for a NASA team, we wanted to kind of evaluate like whether or not this site was the best or appropriate site for future astrobiology research. And so this is part of our team. We had about, I want to say 22 people on the team. This is mostly the caves group. So we've got the MAG team is mostly over here, and here's our caves group, including me in green. So I wanted to start off with kind of the full profile of investigations we did around there, just so you can kind of see what are the things that we can do that help planetary science. And we had 8 science investigations across the entire island. All of it is a UNESCO geopark. And so we got to work really closely with the geopark officials and also the national park officials. So we had, and I'm going to talk a little bit about this area up here. So the La Corona lava tube, you can see La Corona volcano. Oops, I did that too far over. La Corona volcano. We also had a couple of sites here in the middle near the natural part, the Volcanis Natural Park, down in here, and of course we had across the national park as well, and then down here in the Playa Blanca area. So here's our team. Great group of people. We had people from a couple of different NASA centers. We also had people from academic institutions too. We had scientists from all the way from kind of like late career all the way into their undergraduate. So it was really great to have the full span of different kinds of people out there. And like I said, we work with a lot of different support. So we had, the geopark, the national park. We had a local speleologist, which was great to work with. A geologist. We actually had an ornithologist come out with us, who's not pictured here, unfortunately. But the time that we went, we actually had, there was a nesting bird population that's really, really protected. And so he came out with us to make sure that we weren't disturbing any of the birds. And also, I'm sure, to get a sort of an information about their nesting habits. We also had some great partners at ESA, so this is the European Space Agency as well, and the Spanish Research Council. So before I go any further, and I may have said this out loud, I may not have, I'm going to talk a little bit about lava tubes today, and it occurred to me moments before I signed on that maybe not everybody knows about lava tubes. So they can form in a lot of different ways, but you have these volcanoes, as that lava comes down the slope or maybe comes up from below, you can actually, so this lava can kind of form out and then exit the system, leaving a tube behind. So it kind of just like moves out of the system. Or in this one, this is actually from the USGS, you can have this lava that's kind of coming down a slope and melting things as it goes. And so you have sort of this lava river, and then the top can start to solidify. And there's a few different ways that it can solidify I won't get into here. But if that top solidifies and there's still molten lava underneath, it can just continue going until it moves out. And over on the right-hand side, you can see that it leaves this tube. Here's a picture of the inside of one of those tubes. So that's all of us, not all of us, a good number of our group standing in the lava tube. So this is in La Corona lava tube complex. And again, I'm just showing you kind of the similarities. Here we have Mars, we have Lanzarote here, and there are similar processes that form these lava tubes on each of these systems. We just haven't been able to explore them on Mars or the Moon. So I'm going to run through like a couple of the science investigations that we had, and then I'm going to focus in a little bit more on the astrobiology. And so I want you guys to start thinking about, how could this data be useful? Because it's not all about, if we were to do an astrobiology focused mission, the mission wouldn't be entirely about just finding life. It would probably have supporting evidence too. So you want to be like, well, let's say that I do find life. Where does it exist? Is it going to be on the surface? Is it on the subsurface? How did I find that? Why did I think that maybe I should go explore that environment to go find life? So that's that thread that I want you guys to think about as I go through this. So the first investigation, this is really talking about like the volcanism itself. And probably many of us, when we think about volcanoes, we don't think immediately about life, right? But I want you to think about the kinds of environments that volcanoes can produce that could be conducive to life, like a lava tube. So the first investigation here is the magnetic field investigations, and we had a couple of different instruments that we took out. So this is actually the surface of Cueva de los Naturalistas, which is underground here. And so I'm just showing you kind of the field. So if you were to, let's say that you're an astronaut and you were entering this environment for the first time. So you've landed on the moon or Mars, and you're looking out in this environment. Obviously, there wouldn't be any clouds or blue sky here. But how would you even find a lava tube? Sometimes, like, we enter them through what's called a skylight or an ameo. Ameo is just a collapsed feature. So you can do it that way. But how would you figure out where it went? And so our mag team actually is one of the people that they help us do that. So we have the scalar magnetometer here, and he's just got it. There's Jared, he's got it in a backpack, and he walks around and it takes the magnetic field signature of the area. We also have this brand new technology, partially developed by Dave, and this actually takes the X, Y, and Z axes. So this is a three-dimensional magnetic signature of an area, which is, I think it's the only one in the world, is what I've been told. So what kinds of information do we get from it? And the first I'm going to show you is a LiDAR image, because we also took, this is laser ranging, oh boy, and I can't remember, something light detection and ranging is the LiDAR. So this is, yep, it came up. This is just a preliminary analysis. Again, we just went out a few months ago, so we haven't been able to process all the data. So you all are seeing some of this for the first time. And basically, this is where we went in with a LiDAR instrument, and this is the investigator went through and actually walked through the tube and was able to take measurements throughout the tube, and it creates this 3D image of the interior of this lava tube. And so what we're kind of trying to do, and the MAG team is trying to do, is match these two things. So they're saying, okay, well, I'm walking above the ground, and I can get some sort of magnetic reading. And what does it look like in the inside, like in the interior? And so we can kind of start to match, like, how would we be able to use measurements from the surface to tell us about the subsurface? And you can see it's very like tortuous here, not the most tortuous I've ever seen. It does have like sort of branching pathways, which is also a thing that's interesting. So when I think about astrobiology, it's like, well, would life prefer one place in the tube versus another place in the tube? Do they want to be near the entrances, maybe, or do they want to be really in the interior where it's like kind of protected from that external environment? That's the kind of things that I start thinking about. And hopefully this comes up. Yeah, so this is again a very preliminary analysis of some magnetometry data where you're kind of seeing like, okay, here's the tube, and here's what the tube looks like in this super preliminary magnetometry data. This is the kind of thing that an astronaut could actually go do, or even a rover could go do. So another one is the seismicity. So this is like, is there any kind of ongoing seismic behavior of that area? And how can we use that to sort of look at the subsurface as well? In this sense, so you can actually see one of our investigators has this giant sledgehammer and a plate. And you can see where they kind of move the plate along. So what they're trying to do in each of these areas in yellow is go across where they know the tube is. So they know that there's a lava tube underneath there, and they're hitting the plate so that there's some sort of seismic activity, as small as it is, so not an earthquake, it's just a human smacking a plate. And we had already LiDAR images here, and this is sort of a 3D representation of the inside of the tube. So this is blues are higher, reds are lower in the tube. And so they're trying to say, if I were able to do this on the moon or Mars, could I use a similar process to sort of map out where the tube might be? So these are contrasting ways to try to figure out where you are. Now the next one, now we're going to move into like from where is it, what kind of size and shape is it, to what is it like? So we'll start first on the surface. So how does the chemistry of volcanism change along a fissure? And I'll show you first the fissure. So you guys have now seen some of Lanzarote from above, and you know that there are these chains of volcanoes, and you can see all of them in the distance. So they're actually at the top of one, and you can see a volcano, 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 volcano. So there are these chains of them. And so what this team was doing is walking along these volcanoes to see, as that volcanism goes from one place to another, does it actually change in its chemistry? And maybe this is the kind of thing that could be useful for life. So maybe the mineralogy and the way it starts is the best, or maybe it's the worst, or maybe it's a Goldilocks situation. So maybe it's better as it transitions from one state to another. So they're trying to do a similar process. And this team is actually using only handheld tools, so non-destructive. And so this is a near infrared spectrometer. So they're basically, you can see it's like a handheld device, and they're just taking measurements using a handheld device. And the winds were so high this day that they actually had to hold themselves in place. So one of them would have to hold the other one onto the outcrop so they didn't like fly backward. And this is another view of them. So they're also taking this like relief map so they could get these really, really nice maps that we have of the moon or Mars. So then let's go deeper. So I brought up the idea of like, how does the chemistry change? And now let's talk about how the magma itself. So this is the surface. The last one was the surface. How does the surface chemistry change? Now we're thinking about how does that deep magma change? And so what we're looking at here are what called xenoliths. So now we have like that magma starts coming up, but in this particular case, that magma brought up deep, almost mantle material with it. And so it's coming up with the rest of the lava, and it has a higher melting point. So it actually doesn't remelt. And so you end up getting these beautiful green crystals that are kind of within a host rock. And so these are called xenoliths. Now, this investigator was actually contrasting it with stuff that was ejected. So this is like on the left-hand side, these are things that slowly kind of came up to the surface and then became a lava, and then you can actually see them and these little inclusions that are called xenoliths. The other one is tephra, which is ejecta. So this is ejected out from the interior, but that ejecta also has these microscopic olivines. And so they were trying to see like the different processes that occur and how does that change the chemistry. So if you were thinking from an astrobiology perspective, you might think, how does this change the chemistry of a system that might help support life or not support life? So I would like think along those lines. Now we're going to go back into the lava tubes. So we had a team that was, and this is one that I was kind of helping out with here and there. I was also the deputy field lead, so I had a lot of different roles on this particular investigation, which is why I'm talking about all of them, because I helped all of these investigations at some point. So how does the mineralogy and habitability, you guys have probably heard this word a few, I'm sure a lot, change due to proximity to the ocean? So that map that I showed you, and I'll show you again when I talk a little bit more about astrobiology specifically, we had lava tubes, they're all over the island, and some of them go directly into the ocean. Some of them are just in the middle of the island and they're very arid. And then some of them actually have sea air that comes directly into them. And so we were trying to think about how does this help support or not support life, depending on where you are. So this is just one technique. Amy is using that near IR. And then you can, I hope you can see, I know it's very dark in the lava tubes, but Dina is actually, she has this kind of handheld thing that she's pointing directly at the rock. And this is a Raman. It's a portable Raman spectrometer. And I kind of just gave an example, but basically it was like, okay, everything's gypsum, but hey, there's life there. So it's nice that you can see that. She could identify the minerals, but also say, I can tell when there's life. There are a couple ways you can do it. So there's visual ways that you could do that. It could fluoresce, or you could use different kinds of instruments to identify that. My particular investigation, like I said earlier, was like, what kinds of investigations for astrobiology are best suited to this environment? This is an ongoing investigation. There have been a few papers written about this, but we were trying to think, for the kinds of instruments we have, what is the best thing? And so I just want to bring up a couple images. I'll bring them up again. So don't worry if you have questions or thoughts about it. We're going to talk about this at the end. But I thought I'd bring up some interesting things like these are these pink, we don't know what they are. They are pink somethings that are ephemeral. Near as we could tell that they were minerals, Dina is actually doing some analysis of this very soon. We were able to take some samples back. we think that they are some sort of mineral, but when we went back, they were gone. So these are really ephemeral processes, and I think it's one of those arguments that says, we have to be agile in our response to looking for things like life and habitable conditions, because maybe the environmental conditions change. In these tubes, some days they were very humid, some days they were super dry. They were warmer than we thought they would be. So this is an ongoing process that we have to keep thinking about. On the bottom, this is actually an early stage actinobacteria. So they are commonly found in these caves. And, if you weren't sure what you were looking for, you would think, oh, this is just some water droplets that had condensed on this surface. But we happen to have an astrobiologist, one of the preeminent, I think, cave astrobiologists, Penny Boston, was with us. And she immediately said, these are actinobacteria. I know what they are. And if you look at the ceilings, they actually sparkle when you see actinobacteria in your headlamp. So there's a lot of like visual cues for looking for these things. And then something that I was notionally really interested in, I mentioned it before with the seismic or the magnetometry investigation, that these tubes had these really interesting pathways. I had hoped that these were branching at these, but they actually are just a pillar, so it kind of goes around. But it did make me think, if I was a microbe, would I prefer one side versus the other? I don't know. And maybe that's the kind of thing that we need to think about for exploration. And I'll talk a little bit more about this later, but this is just an example of the kinds of samples I was taking. So I was trying to do really non-destructive sampling. So I was taking gases in these environments. And so basically this tube, I would drop it into deep crevasses that I found or back into spaces that you couldn't reach. And I was trying to see if maybe we could identify life from the gases in that environment. And one of the last investigations before I dive more directly into astrobiology is the weathering and dust. So this is really interesting. I just wanted to bring it up as a thing. So near the entrances to some of these caves, they can have really thick dust deposits because there is Saharan dust that moves through this system and can deposit in there. And so you can kind of see really thick dust here. And then as you go in, this is not a trick of the light, it's white. It's very, very light color. It transitions from this really dusty looking color to a yellowish mineral we think is gypsum, and then it transitions into white gypsum for the most part inside the cave. And it's powder. These powders can be very, very thick, and they're formed entirely in the cave. They're not transported in there. And again, this is the kind of interesting thing that makes us think, from an astrobiological perspective, it makes me think, how can these kinds of environments support or prohibit life in certain ways? And then we had a team that actually looked at like how that chemical change. So these are barrancos. They look like riverbeds. There used to be water flowing through them at various points in geologic time, but they are currently arid. So this is a great Mars analog to this particular team. And you can see there's these look kind of similar to that second image I showed you that was the Mars sedimentary deposits. But these are actually all formed by water flowing. And of course, it wouldn't be complete without us being able to explore new technologies. So this is actually an exhibit that's at La Casa de los Volcanes, that's at the one of the visitor centers. Really awesome place. It's on Jamillo del Agua. If you ever get the chance to go, they've just reopened it, and it's a spectacular exhibit. You put on the VR headsets and you get to actually dive through the oceanic parts of the La Corona lava tube in a little submersible. It was really, really fun. But it's the kind of thing that made our team think, wow, what kinds of technologies could we create to do that? And there are technologies in development for that. So it's really inspirational. I thought I'd take a moment. Are there any burning questions on Discord before I sort of dive more astrobiology?
Yes, there's one that came up from Agatha from the UK. She's asking, why do the peaks around 2,200 on the Raman spectrometer graph indicate life?
That's a great question. I wish I had Dina here to tell me that, but that was directly from her. So I think that this is more of a place where she knows from a lot of experience that that's where life tends to fluoresce or make some sort of signal in the ramen. So that I would take it on advisement from a professional. But it's a really good question. A lot of these techniques, especially spectra-based techniques, are going to be based on user experience. So where you have measured samples that you know have no life whatsoever, that are purely mineralogical, and then you've kind of doped them with life, and you start to realize that certain kinds of patterns emerge in that. It's a great question.
Thanks. There's a few other questions, but maybe we'll just do them at the end if that's better.
Yeah, there's not too much more. This is more of a, I want us to, I've been trying to sort of broadly get people to think about how you might look for life and how you might use other data to look for areas that might be conducive to life. So this is specifically the investigation that I was running. This is Dina, actually, so Dina Bauer, Penny Boston, and Mike Spildy. So she's a Raman spectroscopist. Penny Boston is has been exploring caves for decades. She's an incredible astrobiologist, so great to work with. And her partner Mike, out of the University of New Mexico, he's a fantastic mineralogist. So it's so great to have all of their perspectives going into these lava tubes. My investigation was focusing kind of on 3 different kinds of environments. So, and I mentioned this before, the sea spray, so that's actually in the national park. The arid environments, or places that we had thought would be super, super arid, that are in the center of the island. And then La Corona, that actually goes from subaerial to submarine, which is really interesting. Because of the time, I'm going to focus really just on the 2 of these, and I don't have a ton to present, so don't worry. I don't have like 15 more slides or anything. All right, so let's go back to La Corona, and you can kind of see, if you squint your eyes a little bit, you can actually see a little pattern here that shows us, oh, sorry, I'm in the wrong place. Oops, here's the pattern is right here. Still early where I am. You can actually see these collapsed features. Hopefully you can kind of see the openings right here. So these are collapse features that would help us explore this environment. This is kind of what it looks like inside. So you go from like the volcanoes up here, and then you kind of come down the slope. We saw that with the seismic study. So it actually in that red to blue. And there's actually a section of it that has some lakes. They are tidal lakes, which is really cool. I did not get to explore them while I was there. Hopefully someday I'll get to go back. Miasagua is a show cave. They call it the show cave. And beautiful place, great place to go have dinner if you ever want to go do that. That's where the La Casa de los Volcanes is. And then beyond that is the Tunnel de la Atlántida. And this is an incredibly long, I think it's 1.2 or something kilometers long, lava tube that is completely underwater. And there has been mapping done of it. I definitely wanted to go into it, but that was not the kind of permit that I had for this. But it was a great place to go look at. So this is Miasagua, and this is Cueva de los Verdes, which is another show cave. Absolutely spectacular. We did not do science in these areas, but we did go look at them. I know that there have been scientific teams that have gone in to do some microbial work. And in fact, Miasagua, there's these diatoms that only exist there. I think there's little crabs that also only exist in this particular environment. This made the island probably the most compelling from an astrobiological perspective, because almost every different lava tube that we went into had unique biota that exists there. And in some cases, they only exist in that particular lava tube. And so from my perspective, and people have argued with me, that's okay. That's what science is. We can debate. But from my perspective, having a place on Earth that you could go to, that you could treat as kind of an unknown biosignature, made it a really compelling place to go. So this is kind of one of the reasons that we really wanted to explore this environment. This is also I'm going to show a couple pictures of the La Corona lava tube complex. This is kind of further up. And really what I want to give you a perspective of is that in this case, and it's hard to get the sense of scale here, but maybe 35 meters tall. So it's a huge opening to this. And in some places in the interior, they're massive. And in other places, and what you can see here is that someone is crawling through, and there are definitely places where I had to be on my stomach and I'm sliding myself back and forth to get through. So some of these were really restricted environments that would open up into very large chambers. Some of them had various levels of chambers, like an upper part and a lower part. And again, what I'm encouraging you, and it doesn't have to be with lava tubes, but think about the way the geometry of a place could change and how that could influence whether life wants to be there or has an easy or not as easy time existing there. And again, we did not do, there's another group that has done a lot of microbiological studies, so we did not do that. But these are the kinds of things that are on our mind. And along those lines, there are these really interesting minerals. So the way that we think about it is habitability. And you have your host rock with a particular chemistry, and as that host rock changes, it gets modified over time, you can start forming these minerals on the surface, and those minerals could actually be more habitable conditions for life. So maybe they've broken down certain things that might be a little bit easier for life to use. So these are the kinds of things that we kind of pick up on. And it might just be that there's extra energy available in those. And then just to kind of wrap up here, this is the arid environment. So this is in the center of very close to the center of the island, Cueva de los Naturalistas, which I brought up earlier. And you can see some volcanic cones here, sometimes surrounded by farmland. And what I was specifically doing in there was isotopic mapping. This is a technique that I've tried once before in a lava tube in Hawaii, with what you're seeing here. And so the principle was simple, was that the gas, the air, should have a carbon dioxide isotopic signature that's pretty consistent. On Hawaii, it was -8. That's pretty close to most volcanic environments. The atmospheric CO2 in Hawaii, at least, was -8.5, so pretty close. Like they're kind of just outside of error of each other, but pretty close. Now, life should change that by many or several per mil. That's this weird symbol here, which is a per mil. So I'm looking for isotopes. Isotopes, basically, the way they work is that these are microbes. Don't make fun of my diagrams, but they have two different isotopes in them, the 12 carbon and like 13 carbon. Life prefers the lighter isotope, the 12C. And so it will preferentially form itself, and we do too. We preferentially form our biomass with the light isotope. It is kinetically easier than doing it with a heavy isotope. So what that means is that if, depending on what's happening in the cave, so you have to use other data, but depending on what's happening, that biosignature could be plus or minus several per mil. So if it's degrading, you're going to see the light isotopes. If it's not degrading, you might see that it's heavy, because all of these 13Cs are left behind. So again, this is a brand new technique that I decided to try out. In Hawaii, we got some really compelling results, and so we decided to take some. Actually, I didn't intend on taking samples, but the Geopark actually requested that we do so. So I took them for the park while I was there, because they had heard about my research. And this is kind of what it looks like. So we have this weird funnel and a giant syringe, and I pull the gas in. I also do a lot of just ambient atmosphere, and this is me holding my breath and walking through the cave as safely as possible and taking a sample before breathing out and taking another breath. I can do a decent breath hold, which is the only reason I do that. This is the funnel apparatus. And then there's also a lasso where I actually take a 3-meter long tube and, like, I swear to you, an American cowboy, sort of like lasso it into a strange space. And this is used to access small or really unreachable locations. It was a great technique in Hawaii. However, we wanted to be so careful with the ecosystems in Lanzarote that I actually did not use that technique. So I only used the tube to drop into spaces very delicately. I didn't want to potentially damage anything. And then we do a lot of field analyses. So we have this portable spectrometer that we can use. It's called a cavity ring down spectrometer. And then I also take samples back to make sure, since this is a new technique, we're doing this using an isotope ratio mass spectrometer in my lab as well. And that's just my hotel room lab set up in Hawaii that you can see, which I'm sure was very interesting for the cleaning staff that would come in and look at my room. So I wanted to stop us here, and we'll have questions, but I'm going to put up the last of my Slido questions. And this is really, you all can do, actually, it might be better for you all to do this in the Discord if you want, and this way that there's a record for the program. But my question was, how would you look for life here? So I'm going to, put this figure up, but I also want to put up this last couple of figures. So all of these images are taken from Cueva de los Naturalistas, and what you're seeing here, so there's this like kind of deep crevasse, but underneath that crevasse you have these what's called soda straws, and there are these minerals that form in these little soda straws that come down. Here we have water dripping from the surface. This is actually from the roof, I apologize, and also rootlets coming down. So I was shocked to look up and find coming through the ceiling these like super, super fine hairs of roots coming through the surface. And then this mineral that mineral that we talked about before that's ephemeral. So how would you deal with that? And then these microbial mats. So this is an early microbial mat. These end up forming more rigid structures, but this one's sort of like its early version where it's very water rich. So I won't be able to see the answers if you do this on Discord, which is totally fine. So I'll give you guys like a minute to put in some answers, and Tess, if you want to relay some of those, that'd be great. What I'm hoping you see here is that there's a lot of options.
So Judith from the Netherlands said that she would scrape all the surfaces first. Krimesh from Sri Lanka says even if it's a harsh environment there, the water can be seen, and that can be studied in all environments. Kanak from India says mineralogy and microbial interaction. Shriyan from Wyoming says maybe take samples of the surface or air.
So I totally agree with all of these suggestions so far. This is great. And I think many of us would say, yes, let's just take samples of the surface. What I'm going to challenge us to think about is how can you do this non-destructively? And that's really, really hard. And I think going to this environment, so going to Lanzarote this summer was transformative for me in many ways. And one of them was in how delicate these environments are. I really did not appreciate it as fully until I was able to go there. And actually, I'm not allowed to show you all some of the most protected caves because this is an open forum. But there are some environments that even just putting your boot in the ground was like tremendously damaging to the environment. And so it really made me gain this appreciation for how much of a privilege it was to even be granted access to some of these environments, but also how can I protect them? So if I'm going into a planetary environment for the very first time, I think that this is a Bethany opinion and not necessarily all of NASA opinion. So please be aware of that. Bethany's opinion is that we should take every opportunity to protect the environment first while getting our data. So I'm challenging all of us, including myself now, to think of ways that I cannot go in with my rock hammer or my chisel and just start scraping things off the surface. It is, at some point, it's how we're going to have to do this, right? I completely agree that probably, I don't know all of the curriculum that you guys have gone through, but probably there's been a lot of talk about like genetic sequencing, and you have to get physical samples in order to do that. So how can you do that without taking from the surface? Could you do that without having to destructively sample your surface? Which is hard. Maybe you could do it from the air. So I like the suggestion. I haven't tried, but it's a really good idea that maybe you could do it from the air. Maybe there's enough just microbes floating around. At least in Earth. Earth would probably be a good place to test that out. I don't know about any other place. Any other suggestions, Tess?
That looks like the most serious one of you making jokes and suggestions. Sarah from Mexico says maybe we could try to analyze the environment by using sound waves instead of movement to map the surface.
Ooh, interesting. Okay. So it'd be like an echolocation sort of thing.
That would be amazing if it works.
That'd be cool. I think that there are processes like that, like radar sounding. I think you can do that. So that'd be pretty cool. Well, I know this is a
Yeah,
big
but
question. I'm not saying everyone needs to solve it today.
uh,
It'd be
yeah,
great.
definitely really good to think about. I think it's very important because I think we do very often just kind of want to go in there and get the best science we can do without thinking about where we're going.
Same. Yeah. And I know when I've gone to other places, that's just kind of how I'm taught to do it. So it was a really great experience to have to go with the NASA team who had a ton of handheld non-destructive techniques that we could try in these environments. So that was a really cool experience. Are there other questions? I know I gave a little bit of extra time than I thought, but or I intended to have more time than this, but happy to field other questions.
Yeah, if you have a few extra minutes, there's a few that people are asking. So Sarah from Mexico and Mingyu from Sweden are wondering, how do you account for a difference in radiation or atmosphere between Earth and Mars when doing field work?
That is a great question. There's a couple of different things you can do. So one of the, I think, advantages of lava tube research that I'm discovering is that and this is a great picture for this actually. So all of this overburden here, this material that's above the lava tube, it actually protects the inside from radiation. It's one of the arguments that many people have made to say that this could be a great place to support life on other planets and moons because you'd be protected from radiation. So that's one of the reasons that I particularly find it a compelling place to go. Now, the surface, I know that with the Mars missions in particular, they have focused a lot on like drilling through that surface material that has been bombarded by radiation. So that's kind of how they meet that challenge. The other way you can do it, and this is getting into my lab work, is that we could take samples that we think are analogous to the kinds of things we might find on Mars or the moon or wherever. I do a lot of Europa work. I know I've been talking about Mars all day, but almost all my work is on Europa and Enceladus. And you can subject those samples to radiation in a controlled environment and kind of see what are the changes, the chemical changes that occur. You could do that with its genetic code. So how does it break? Like its genes break up? Like what does it look like? Does it turn on new kinds of genes as a response? So these are like really interesting questions that need to be sorted out.
Thank you. So Ramita from India is asking, how do you choose a particular site to explore on Earth?
Great question. There's a lot of different ways that you can do that. And I think most of it is it's the question that you're trying to answer. So I have some sort of scientific question, and I think that then you have to go find the right place for that question. So maybe my question is, what is the effect of lava tubes environments on habitability? And so this is a good question that many of our GIFT researchers have looked at. And so we looked at a few different lava tubes, and then we have to find, well, what is the most Mars-like? Because we don't think that the moon has any life on it, but what's the most Mars-like? We've often gone to Hawaii, so Hawaii has great lava tubes. Some of the right place question is it accessible? So some of these places, like if you have to be helicoptered in, or if it's incredibly dangerous for you to be there, maybe that's just an accessibility issue. Sometimes it's a right environment. So Lanzarote is perfect for me because you have those dust storms. You can actually see them in the background. It's really hazy that day. So these dusts coming in from the Sahara, high wind. It's very arid. So this was like, to me, a really great Mars analog environment. But there's a lot of things at play, and a lot of it is your question: how safe is it, and how accessible is it? Can I even get there?
Very cool. Okay, so I think we're out of time, unfortunately, but thank you, Bethany, for sharing an hour of your day with us. This was really great. I learned a lot. I'm sure everyone else did as well.
Well, that's great. Yeah, and I put my email address there. I'm actually heading out in the field. I'm camping this weekend, and then I'm heading out in the field in a couple weeks. So if it takes me a while to get back to you, it's nothing to do with you. It just happened. I'm just out in the field again. But yeah, happy to take questions offline if people are interested. And I will send you guys that word cloud if I can download it.
Sounds wonderful. I'm glad we caught you before you head to the field. I hope you have a really good trip. Where are you headed?
Yeah, me too. New Mexico this time, actually.
Nice.
It's been a while, many
Very
years
cool.
since I've been to New Mexico. I'm excited.
That's awesome. I hope it goes well.
Yeah, thank you.
Okay,
Thank
well, we will stay on for flash talks with everyone else, but I think we can thank Bethany.
All right, thank you. And have a great day. Thank you for inviting me. I really appreciate it. And thank you for your responses. Those of you who were able to respond, I really appreciated the interaction. So, all right.
Thank you.
Thank you, everybody.
Bye.